Hello again, ladies and gentlemen. Today we meet again to discuss about the topic that is the shear, which we call the shear force diagram and the bending moment diagram. Okay, I have to actually emphasize this is just a method on how to achieve it. Is that we generate a function or equations for them. Okay. Well, let's talk about what it is first. The shear force diagram is stand for, or SFD stand for shear force diagram. Okay, the diagram of the shear force, the picture of the shear force. Okay, the BMD stand for bending moment diagram. The diagram of the bending moment or the picture of the bending moment. In fact, we are talking about two graphs. One graph is the graph drawing the value of the shear force. The other graph is a graph showing the value of the bending moment. Okay. Now, before we move on, then we talk about reason. Why do we have to draw this graph first? Okay. Then we will start talking on how we should draw a graph or how we should draw graphs. And then we'll see the example on how we actually do it. Okay, the reason. Apparently the shear force and the bending moment are the common features, are in fact the major features that cause the failure in structures. Okay? Then the bending moment also cause about 90% of all deformation in general, in the general construction, in general structures, right? Usually we call rigid joint structure, where the joint do not rotate. Okay. Then, because we need to control both, of course, the failure of structure. In fact, we have to control it not to fail, right? This is about safety. So we need to be able to know how much it can take or how much it has to take, so we can design the structure to be able to cope with that kind of internal forces. Okay? And of course, we need to control deformation, because too much deformation will cause, one thing is the small displacement theory cannot be correct anymore. Second is that it doesn't look really safe. I don't want to walk in any building that is the beam bends so much or the column twists so largely, so many angles. You know, it's just not pleasant to say, right? So we need to control them. Okay? If you remember here, now this is the problem. This is the example from the last lecture, the example 1. When we do point A and point B, notice even though in this case the axial force is constant, the shears are not. Right? 40 at point A, 60 at point B, direction change as well. Bending moment as well is not constant. Bending moment at point A 100, bending moment at point B 60. So, how do we know where is the maximum, where is the minimum, where it can change direction? Right? We are not going to calculate every single point indefinitely. So the idea is drawing a graph and then we can tell everything. Right? So that's the idea. As I said, it's change, and therefore graphs in fact are the solutions. So that we can tell shear force at every single point on the structure and the bending moment at every single point on the structure, meaning we can design the structure to resist those shear force and those bending moment and of course axial force as well. Okay, move on. Then, how do we draw a graph? No matter what technique we use to make sure a graph makes sense, then you need to have, for mechanics, you need to have units and directions. Okay? Like bending, sliding or sag, shear force, which side is up, which side is down, right? Something like that. If it's axial force, with it tension or compression, okay? Assign the positive on one side, negative if it's opposite, per se. Okay? Then of course, for a graph to make sense, we must have the beginning point, the end point. Okay? Which of course in this case with the structure. And then we should tell all the peaks, high and low. We have to tell the low peak because in fact negative positive in mechanics doesn't mean negative is less than positive though. Negative is in fact the opposite side, the opposite way, not less, could be higher. For example, tension of 10 plus 10 compression of 100 minus 100. In fact, in this sense, minus 100 is bigger than 10 because it's only changed from tension to compression. It doesn't actually govern by the negative, positive in normal mathematics sense. Okay? So we need to know high and low. And of course, in some part, we can make it smaller if it's lower, meaning we can save money, save material as well. Okay? So we only need to do big cross section on a big forces, basically, big internal forces. And of course, we have to tell the position of zero value because that is when it changed from minus to plus or change from plus to minus. Okay? It is this point, the direction change. We need to know them too. How about this one? Let's try simple example. This is a cantilever beam, support at point A with a fixed support, of course, a force acting on it. Okay? What we want to know now we want to know everything, every single point of shear force, every single point of bending moment. So we use the graph, draw shear force diagram and bending moment diagram. Okay? Well, you choose step, find reaction first, draw the free body diagram, put in the reaction, the unknowns, 3 equations, 3 unknowns, we can solve all the reactions. Okay? If it's going too fast, you should pause. Okay? I mean, you can pause the video, you know that, correct? So, if I'm going too fast, you have time to look at it, then you just press pause on the video, please. Okay? Then, once we get all reactions, then we try to generate a function. Okay? We cannot cut at a point anymore because we need a function with the length of the beam. So we cut at the general distance we call x. Okay? It is not half length, it is not a quarter of a length, it's not the full length. It is somewhere in between, right? In between A and B, right? We don't know where. So we just call it x, and we substitute x when we want to know the point. Okay? So, but the internal forces are still 3 of them there. Before we put in this one to draw a graph, this time we should assign positive and negative direction first. In this time, I will use this positive direction for shear force and the bending moment. Meaning, notice, the sign convention will follow what I just assigned. Okay? On the right hand side of the box is down. This one here, the shear force is on the right hand side of the cut. Therefore, it correlates. Right hand side and right hand side. Right? Okay. Then the bending moment, the same way. There. If we do sigma Fy, then we get the shear. If we do sigma moment about point B, you can do about point A, but it will be more complex in many cases. I suggest you do at point where you cut, but your way, you can have your way. Okay? Then we can get the bending moment. Notice this time here is a function because it's stuck with the term x. Because that force, there, that one comes from the moment. Moment doesn't time distance to be a moment, it's already a moment, so you just put in there. Now that force there apparently is a force. To make a moment, you have to time it the distance. In this case, the distance is x, correct? That's where the x comes from. And of course, lastly, the bending moment itself. And therefore, here we are. Now, because we want to solve for the bending moment, we move everything away from one to the other side, leave bending moment on the left-hand side, of course. Now, so these are the 2 values that we need to draw a graph. Okay? Now, so once we get the functions, then we move on. Okay? Because we have 2 graphs, it will be clear later, right? But at this time, take my word for it. Shear force diagram will always be easier to draw than the bending moment diagram. Well, always? I think always, but just to be on the safe side, most likely. Very, very extremely likely, per se. Okay? So, this is the body. So, not only the body, the beam. We just put in the beams to make the axis of the length for the graph, right? So, basically, at the beginning, we talk about point A. At the end, we talk about point B. Okay? So, now, as I said, we need a unit. So, kilonewton we already have. We need direction to draw a graph for mechanics, right? Okay. Step 1. What do we want? We want the beginning and the end point. With this equation, apparently, it said is a constant, meaning at A, it is the same, 173.2. At point B, the same. And I said there is no x term in here. Therefore, it is a constant function. There. Of course, if it's constant, therefore there is no peak, there is no zero. It is only one value in this case. So we can ignore step 2 and 3. Okay. What about bending moment? Again, the same. Coming up with the bending moment positive sign first. Then, well, don't forget that one we already assigned it when we start calculating the function. Okay. So we keep on with that sign convention. We say positive already. Then the function is this one here, right? Now, what is the beginning point? Beginning point is point A, where we assign x, remember, x starting point from A, therefore at point A, x equal to 0. Substitute into the equation, then we can work out the bending moment at point A, okay? And then we mark the beginning point. The end point, point B, the x is 4 meters. Again, substitute into the equation, then we get the point, which is 0, right? If it's 0, then it touches the axis, no problem. Now look at the equation. The pattern of the bending moment equation is in fact what we call straight line function, meaning it is straight line, it's no parabola, right? How do we draw straight line function? We know the beginning point, we know the end point, we just draw a straight line connecting them, and then we have that one there. Done. So these are the two graphs. One, no, this one is minus, the shear force diagram, bending moment diagram. And that's the answer. Okay, let's look at another example, shall we? A little bit more complex this time. We use distributed load. Okay, the same concept happening. What we want is we want to draw the shear force diagram. We want to draw the bending moment diagram. Yeah. The first step, the same as before. Then we find out all reactions first. Free body diagram, 3 unknowns, 3 equations. Then we get all reactions. When we get reaction, notice one thing though. In this case, if I cut the section between between 1 and 2 and draw the left hand side picture, I only see AX, 1x, 1y, and 120 kilonewton per meter, right? But if I move across point 2, cut between 2 and 3, then we need that R2 as well, meaning these two sections has two different force system, meaning it will create different equation for shear and different equation for bending moment. In this case, we need 2 sections for shear and 2 sections for bending moment. Then I will start with from 1 and 2. There we are. Again, we don't want to cut at point 2. We want to cut somewhere in between, not in the middle, not at the point, it's just in between. So we can assign x. Then assign again the positive sign convention. Then we put in the unknowns. Once we got all the unknowns down, then we can calculate again 3 unknowns, 3 equations. Then sigma Fy give us the shear force equation. This time we get equation though. Okay. Then the bending moment, again equation. This time notice the x square, meaning it's parabola. Okay. Then notice that the shear force is straight line function, the bending moment parabola. So the shear force by concept should be easier to draw than the bending moment still. Now from 2 to 3, notice that the sign convention I will remain the same because otherwise it will be too confusing. Okay. It will remain the same as the first picture, at the first part. Okay. Then we put in accordingly. Then sigma Fy, we get the shear force. Sigma moment, again about where you cut would be, that is not 2 prime, my apologies, that should be 3 prime. Okay. Sigma moment about 3 prime. Okay. And then we get bending moment 2, 3. Now, notice that we have the shear force between 1 and 2. We have the shear force between 2 and 3. So we are ready to draw the shear force diagram. We have the bending moment from 1 to 2, and we have the bending moment equation from 2 to 3. So we are ready to draw the bending moment diagram from the whole beam. Okay, so this is ready to draw the graph. Let's start from shear force diagram. Easy one first. Okay, the same way I am thinking. Axis come first, and then of course the length from 1 to 2 and 2 to 3. Okay, now from 1 to 2, that is the equation. Okay, the beginning from 1 to 2, the beginning is point 1. Okay, because that is x, 1, 2 starting. Point 1, then x equal to 0. And then we can calculate the shear, substitute 0 into it, into the equation. Okay, mark it the beginning point. What about the end? The end is 0.2, right? It's again from 1 to 2 first. So the end is 0.2, x therefore 4 meters. Substitute into it. Then we can calculate what is shear at 0.2, mark it at the end. Look at the equation. The pattern is 144, a constant, minus 96x. A constant minus another constant times x. This is straight line function. We have beginning point, we have end point. Draw a straight line connecting them. Notice it cuts 0. Remember, there is no peak, so number 2 can be ignored. Number 3 said, give the position of 0. That is 0 value there. Okay. This equation, however, can work two ways. If you know x, you can find shear. If you know shear, you can find x. In this case, where it cuts 0, we know shear is 0. Therefore, we substitute shear 0 into the equation and work out x, in this case, 1.5 meters. Done with 1 to 2. Next, from 2 to 3, that is the equation we worked beforehand. Again, point 2 to 3. This time the beginning point is 0.2. However, because we measure point x 2, 3 from 0.1, when we come to 0.2, x at 0.2 is not 0, but at 0.2 is 4 meter. Substitute into equation. Then mark the beginning point, 192 kilonewtons. Then at 0.3, x at 0.2 is already 4 meter. Move on 2 more meters to 0.3, then x becomes 6. Substitute into equation. Apparently it turned out 0. And of course, again, the pattern of the equation is a straight line function. Draw a straight line connecting them. That complete the shear force diagram. Okay, then should we move on? Okay. Plus, minus, plus. Okay, just to make sure that we know what we talk about. What do you mean plus? Plus meaning it behaves in that the same as that shear box. Minus, opposite way. Okay, that's all. Now let's move on to the bending moment diagram. That bending moment positive sign has been assigned since we calculated the equation, remember? So we keep on with the sign convention. Axis 1 to 2, that is the equation. Again at point 1, oh well, we start x1, 2 and x2, 3 at the same point, so might as well mark them together. At point 1, x is the beginning, is 1, end is 2 at the moment. So beginning 1, 0, substitute into it, we get bending moment equal to 0. At point 2, substitute x equal to 4, then we calculate negative 192 kilonewton meter. Okay, mark it anyway. Now, because it's parabola, there can be many ways. Okay, so we have to find out the slope. Because we don't even know whether it go up first and then coming down, or it's coming down straight away. Okay, the shape of the parabola could be either the bell shape, right? The normal bell shape and the upside down bell shape. Okay, which one we don't know. So we find the slope first, trying to explain it. Okay, there we are. Now, how to find slope? Then we differentiate it with the variable. In this case, the variable is x. So we differentiate it with x. Now, if we look at the equation closely, apparently that equation, the equation of the slope, apparently it is matching with the equation of the shear. Okay. I'm not saying that it will always be like that. I'm not saying that yet, because I haven't proved it yet. But at this moment in time, I know that between 1 and 2, I differentiate bending moment, I get slope, which is exactly the same as the equation of the shear. So I will use the shear as the slope of the bending moment for now. Okay. So there, that is the shear force diagram. What does it tell you? Or in fact, I should say, what does it tell us? It said that at point 1, the slope is positive, right? Because shear is positive. Shear is the same as slope at this point in time. If the slope is positive, meaning the value of bending moment has to go up until 1.5 meter. The slope becomes 0. What does it mean? It means it hit the peak. Because it's going up, therefore it hit the maximum value, meaning it stopped going up from that point. After 1.5 meter, it is actually coming down, right? Moreover, at first, at point 1, it increased really quickly because it's highly positive. Up to 1.5 meter, it becomes slowly increased and then become no increasing. After that, it reduced slowly and then increased quickly at point 2. Okay, described like that. Okay. It's also written on your handout, so you can read from there too. Okay, meaning when I draw it, remember it go up until 1.5 meter, meaning peak is there, as we said. So we can substitute 1.5 into equation and calculate the value of the bending moment at that point, which is the peak bending moment, the maximum per se, at 1.5 meter. Okay. At first it increased quickly and then stop increasing. Then getting down slowly and then getting down quickly, it becomes there. Okay, that shape. Now apparently without knowing, we already mark number 2. We calculate the first point, the end point, we mark the peak, right? So number 2 is done, tell the peak. Number 3, however, isn't, because apparently we have cut 0 here. Again, this equation, BM12 equation, if we know x, we can find BM. The same if we know BM, we can find x. We just substitute BM equal to 0 into that equation and work out x. If BM equal to 0, then x is 0 or 3 meters. 0 is at point 1, 3 meters is where it cuts 0 there. Okay? So that is 1 done. 1, 2 done. Next, of course, 2 to 3. Equations here. This one again work beforehand. Don't forget x start at point 1. So at the beginning point of 2, 3 at point 2, x is not 0. X is 4 meters. Substitute into equation, then we can get bending moment. Apparently the same value, 192 minus 192. So it's the same point. Then at point 3, it equal to 6 meters. And substitute it, then we have bending moment equal to 0. Again, the shape of the equation is parabola, meaning we have to talk about slope again. So if I want to talk about slope, I have to differentiate the equation with the variable. In this case, differentiate bending moment with respect to x, of course. There. Look at that equation. This is the equation of slope. Guess what? It is the same as the equation of the shear between 2 and 3. In this case, again, I'm not saying that they will always be the same, but I will say in this case, it is. If in this case they are, it means that the shear is equal to the slope of bending moment for this case. Therefore, I will treat it as such. Between 2 and 3, it only increasing. At first, increasing quickly because it's positive a lot. Then it stopped. It slow down and slow down and slow down and then stop increasing at point 3, meaning at point 3 is a peak. Okay? And therefore, it is in this shape. and therefore there is no peak. In fact, peak is at 0.3, which we accidentally find out already. Then there is no cut signal. Well, there is cut signal at 0.3, and again we already define it. Therefore, that's done. Mark the positive, negative, just to be sure, and let's summarize what we found. That is the case. So, that actually concludes the lecture for today. We learned first why we need the SFD, shear force diagram, and the BMD, bending moment diagram. Why do we need it, right? Then we learn how to draw it by generating equation, or we call it by functions. We create the equation and draw the graph according to the function we have, or the equation we have, right? And then with these two graphs, we can tell every single point of we can tell the maximum, the minimum values. We can tell where it cuts zero. We know everything, basically, about shear force and about bending moment within the material. And as I said, that's the conclusion for today. Thank you. And hopefully I will see you again in the next lecture. Take care until then. Bye-bye.